Have you ever played a game against someone who is much better than you? It's not much fun, right? At first you think, maybe I can pull out a win, but then after a few tries you start to realize that there's no chance and you give up. Okay, so what about playing against somebody who's much worse than you? Surely winning is more fun than losing, right? Maybe at first, but after a few games you start to get bored. So what gives if winning is supposed to be more fun than losing? The fun of games is the tension building and building and building as the outcome becomes more uncertain and ever closer. But that tension is really hard to build if you already know what the outcome is going to be. We have the same player and opponent balancing act in a single-player game, only the opponent has to be modeled inside of a computer. In my mind, this presents three problems. 1. Adaptation. A computer can't do anything but respond to its own programming. It can't adapt to new circumstances. 2. Anticipation. Trying to program for every possible circumstance or choice a player might make is a really large task. 3 is computation. Computers have limited processing power, so every task you ask it to do has a cost on the frame rate of your game. So, how do we make enemies think convincingly without god-tier CPU or an army of programmers? Let's talk about it. I'm Dryden Thomas, and this is the third devlog for Lighthoof, a melancholy Metroidvania focused on zippy combat and tight platforming, where you play as Lighthoof Noah, our skull-masked, deer-footed hero, with his floating light arrow as he explores the secrets of a land strangled by deadly fog. If that sounds cool to you, head on over to Steam and give it a wish list. I'm working on finishing a demo right now, and I am so excited to share it with you. Okay, problem 1. Adaptation. Let's flex on computers for a little bit. Say you're walking down the street and a stranger comes up to you. Maybe they start yelling at you. You have all kinds of options. You can ignore them, run away, yell back, try to get them to calm down, call for help. You're going to read everything about the situation, and you're probably going to do what you think is best. On the other hand, if a computer is minding its business, doing its program, and you yell at it, it's not going to do anything. Believe me, I've tried. What do we do with a system like that that only does what its programming tells it to? One possible answer here is a programming pattern called a finite state machine. State machines can be like the brain of an enemy. You create these simple states, and then you create pathways between them so that it can transition to a new one when a certain event happens. Here's an example. If I'm in the kitchen chopping vegetables, I might be in the cooking state. While I'm in the cooking state, I'm going to follow the instructions on the recipe until the dish is finished, and then I'll probably enter the eating state. The dish being finished is the event that takes me into the eating state. But if I'm chopping vegetables and I start to hear my dog throwing up in the other room, I'm going to very quickly transition into the get my dog outside state. By simplifying what happens in these states, we might not be able to capture all the nuances and multitasking that happens in the human brain, but we can pretty roughly model the decision-making process. And that's what it's all about. Problem number 2 is anticipation. A perfect enemy AI would be given a viable move for every possible game state, and it would have access to all of the best strategic information to make the best decision every time. We've made this before. Deep Blue is one of the most famous AI systems of all time. It was designed to play chess, and it was the first one to beat the reigning champion, Garry Kasparov. It also took 12 whole years of development to get to that point, with a team of some of the world's most brilliant computer scientists and analysis from hundreds of thousands of Grandmaster games, as well as human input from Grandmasters themselves. Luckily this time, we don't need an algorithm that can outplay any human. We just need one that's a viable threat at any given time. So let's solve this problem by simplifying the possibilities and giving our enemies the minimum information they could need. A good starting point could be knowing about the player's location. If you're gonna attack something, knowing where it is a good start. This simple enemy, the bone bat, changes to its attacking state when you get close enough, and then it moves toward you. If you get far enough away, it gives up and it stops chasing you, returning to its patrol state. That's it. Okay, but what if we want to be able to hide from an enemy? It shouldn't be able to see you if you're behind something, right? Well, okay, we can add a second test that checks whether something is in the way. And then, what if we want it to navigate around obstacles? In that case, we're going to need a pathfinding algorithm to calculate a pathway to the player. Well, what about grounded enemies? We can anticipate some of their needs too. By keeping an eye on ledges and walls, we can tell them when they need to enter a turn state and switch directions. Let's get more complex, up to the boss level. A boss has to be most like a human opponent, offering a continuous challenge that doesn't let you disengage. It's going to be the ultimate test of our state machine system. How disappointing is it when you can cheese your way through a boss just by sniping at range or by spamming one overpowered attack? We have to give the boss enough moves and enough information to keep you from doing that. If we put an attack select state between each attack, we can use the player's position and the positions of surrounding terrain to make a decision about how to attack. We'll run through all the possible next moves and remove the ones that don't make sense. For example, if the player is far away, we don't want to use a close melee attack. And if the player's close, we don't want to use an attack with a long windup that'll give them openings to just hack away at us. And as a finishing touch, we don't want to be seen using the same attack over and over, because that will make us look boring. Let's keep a short list of recently used attacks and remove those from the pool as well. We can also take out attacks that we don't want to use yet, like if we've got a powerful finisher that we want to keep hidden until we're at low health. With this remaining pared down list, we can choose a random attack. Then, when it's over, we go back to the select state to repeat the selection process. Well done! We have now successfully modeled a decision-making apparatus so that our enemies look like they know what's going on. And there's way more that you can do with this. One of the most common state-changing variables that I see in games is awareness. Your character can be making noise, or in view, or out of view, or in stealth, or out of stealth, and that's going to affect the enemies around you in their awareness of you. If they cross a certain threshold, they'll change from a patrolling state to an aggressive state. Another type of decision an enemy might make is if it's low health, they might start trying to run away to save themselves. This also makes them look pretty smart. Any variable that you can think of to track can be used to make decisions if you write your code in the right way. But it can get to be too much, and that's what brings us to our third problem, which is computation. By now, you've probably seen the swarms of enemies in Vampire Survivors, even if you haven't played it yourself. As a group, they're intimidating, but each one on their own isn't much of a challenge. They're not dodging your attacks, using feints and blocks, or anything that makes them seem especially aware of your strategy. And that's because that much processing would completely tank your frame rate. In programming, code that has to be run a lot of times every frame is called a hot path. If each enemy in Vampire Survivors were running its own decision-making algorithm, and there were up to hundreds of them simultaneously doing this, that hot path would get very, very crowded. So we just gotta find some slick ways of cooling it down. While I don't usually have more than about a dozen enemies on screen in Lighthoof, I've still found some ways to optimize my enemy thinking so that I can save on processing power. Here are 3 of them. Number 1. Delayed decision making. Lighthoof runs at a minimum of 60 frames per second. An average human reaction time is 1/4 of a second. That means that I don't need to check for each state change condition every single frame to make it feel believable. By setting my enemies' brains to check for state changes every 1/10 of a second instead of every frame, I'm automatically cutting their processing demands down by at least 6 times. Number 2. Limiting possible next states. In my first try at creating an enemy brain, an enemy would calculate the player's relative position every single frame, whether or not it needed to use that piece of data. In the current version, I only have it calculate that if there's a possible next state that depends on that information. Here's an example. An enemy might need to know how close the player is when deciding what attack to use, but once it's decided, it can carry out that attack without that info. Cutting unnecessary calculations like this can save a ton of CPU time. Number 3 is using events instead of constant calculation. Okay, I lied a little bit. I've been talking a lot about calculating the player's position because it's a really simple example, but I don't tend to do that very much anymore. Now, I mostly use this thing I made called a player detector that sends a signal to the enemy brain when it, you guessed it, detects the player. It's kind of like telling your friend to just text when they get to the door instead of texting them 60 times per second to ask them for their current position. Optimization is a huge, huge topic, complete with disagreements and lore and mathematics and exaggerations and new discoveries being made all the time, but hopefully this has at least been an interesting little dip into some of the tricks. So what do you think? Are you left with any burning questions about enemy AI? What games do you think have done an amazing job with this, or a terrible job? I love discussing stuff like this, so kick something off in the comments. And if you've enjoyed this series so far, please go ahead and subscribe and hit that notification bell. See you in the next one!